Today we will talk about hybrid systems. So if you're studying the master program, you have taken courses in modeling and simulation. So you have talked about continuous dynamics, differential equation, difference equations, and you have also taken another course in discrete event systems, where you learned about state machines. And what we will try to do now is to bring these two different worlds together. And there is a very good reason for that. And that is because mainly all systems that we need to simulate and design controllers for are of this hybrid nature. They have continuous dynamics described by differential equations, and we have discrete behavior. And it turns out that these hybrid systems are much more complicated to analyze. I mean, if you have finite state machines, then you can do, especially if you have a finite number of states, then you can enumerate all the different states. You can try to be smart about it, but there can be a large number of states, and then you can use different techniques to deal with that. But in principle, it is at least theoretically possible to enumerate all the different states and say if a property is fulfilled or not. And when it comes to continuous dynamics, we know that as long as you have linear dynamics, for example, we have a lot of very useful techniques to reason about these systems to prove stability, etc. Non-linear systems is a little bit more tricky, and that's why we have a separate course on that. But even if you just start to combine linear dynamics with discrete states, and you start to switch between different behaviors that are linear, strange things can happen. And that is what we will talk about today. And this has practical implications, because when you will start to simulate hybrid systems, you need to be aware of that these problems that we will see today, that they can show up and how to deal with them. So, but first I just wanted to do a little bit more on the motivation side here. So, since we are talking about closed loop systems, so we have a controller that is deciding on control signals for a plant, and we get some outputs. And then we have some feedback loop like that. So this is a very high level perspective, right? So when we're going to simulate this, the plant here, that is governed by physical relations, typically described by differential equations. Okay, so we have physics here. And here we have our control algorithms, as you know. And if we start to think about where do we have continuous dynamics? So it can be continuous time or discrete time, it doesn't matter. Of course, we have it here, right? So the control algorithms, if you have a PID controller, that is a differential equation. So we have it in the controller. So we have the PID, we have LQ, it can be some form of model predictor controller, etc. Okay, but we also have it on this side, right? So, and here we have Newton, Euler, Kirchhoff, the different laws that describe the physics. right? So, and where do we have the discrete dynamics, the state machines? Okay, so when we start to think about it, we have it in the controller. So we can have, for example, different modes in the controller. So the controller, so a typical feature of industrial controllers is that they can be run in automatic mode or in manual mode. So when they run in manual mode, it's for the operator to take over the control action and decide on the control signals themselves. So then we switch between two different modes. So we have different modes in the controller. So it can be manual or automatic. So we can also have that it will do one thing during startup and then something else during normal operation. So startup, normal operation, and we can then also have other types of, we can have economy mode, sport mode, for example, if we are designing a cruise controller for a car or something like that, right? So we have different modes here, but we do also have different modes in the physics. So of course, in the discrete event system, you talked about that machines, they can be idle or they can be operating, right? So on and off. And then you will have different equations that describe what happens. So this is some form of different subsystems can be activated or deactivated. But we can also think about, for example, if we have are building a model of a human, right? So if I'm standing on two legs, I will have some form of dynamics. If I'm on one leg, there will be another. And if I'm running and I have no leg in there, or no foot in the on the floor, that will be something different, right? So for example, then we can have standing, walking, running, for example. And this is just a special case of if we have mechanical motion systems, then when the different subsystems they collide with each other, new things will happen, right? And if you have electrical switches, they can be on, closed or open, for example. That's another type. Okay, so we have discrete dynamics in the, or different modes at least, in the plant as well. And if we now go back to the controller again, we can start to think about, so the control algorithm we have designed, they will be implemented on something. So today they are always implemented on a microcontroller, right? And on the microcontroller, it can be that it's not only a single control task that is implemented on that microcontroller. There could be many of them. So that's why we have real-time operating systems with schedulers. And the scheduler, we will talk more about that later, but the scheduler will be responsible for deciding among all the different control or all the different tasks that would like to execute, who should be allowed to execute on the processor at a certain point in time. So So the controller is executing on a microcontroller. And several controllers can execute on the same microcontroller. And real-time operating system so abbreviated RTOS is used to schedule the different control tasks. And it can be other tasks as well. So it can be logging, for example, or graphical user interfaces, or communication tasks. So it's not necessarily only control tasks. But the conclusion here is that real systems, they have continuous dynamics, discrete dynamics in both the controller itself and in the plant. So, so real systems consist of both continuous and discrete dynamics. Okay. So this is something we will talk more about in the course later. So we will go through this, how you can implement microcontrollers using C, how you can build up a scheduler, how it works, different problems you need to deal with when you implement control tasks in this way. But the basic message here is that we can't avoid having to deal with hybrid systems. They are basically everywhere. And as we will see, hybrid systems are really tricky to analyze. So we need to be really careful when we deal with hybrid systems. So we will first start with, and I think also Bengt in the discrete event systems course talked a little bit about hybrid systems. So I think we will go a little bit deeper here. So this is a topic that there are many things to say about, and it could be its own course. But we will just give you the big ideas and problems here. Okay, so basically, modeling of hybrid systems. So we have differential equations plus state machines. So if we combine them, we get something that we can call a hybrid automata. Okay, and we will just give you an example here. So we will use something very simple that is easy to draw on the blackboard. So a switching thermostat. So it's not a very exciting problem, but it's illustrative. So it will have two different modes, we will say. So it will be off, and it might be on. And within each mode, we will have a differential equation that describes what will happen with the state variables. So let's say if it's off, in this case we will have a constant, let's see, so T dot is equal to minus K2. So it meaning that the temperature, in this case, it will drop at a constant rate. Okay, right? And then it can switch back and forth between the two modes. And if we are in this mode, we will have another differential equation. So this is just some arbitrary example, but K1 and then 70 minus T. So the closer we get to 70, the smaller increase of the temperature we will have. And then we will have different guard conditions. So we say here that the temperature T, in this case, so this transition can happen if the temperature is below 62 degrees. And this one can happen if it's above 68. We will see. So these two are the different modes. That one and that one are called guard conditions. We will have our differential equations. So it can be described as a vector field. We'll come back to that in the definition. We will also have something here that are what is called the domains. So this mode, so it can only be in this mode if T is less than 70. And in this mode if T is larger than 60. And then we have some, let's say this is the initial mode, and then we need some initial temperature as well. So it doesn't necessarily have to be a fixed initial temperature. It could be just a constraint saying that T is between 60 and 70 when it starts. So this, because you might not know, right? If you model some physical system, you don't really know what the temperature will be. So you would like, if you have some properties that should be fulfilled, you would like them to be fulfilled if the initial temperature is in this range, for example, no matter where you start. You see, so initial conditions. Okay, so we had a few properties here. So in this case, we could have multiple initial values. Right? And it is not fully specified what will happen or when a mode switch will happen. And think about events in the discrete event systems course. You have, for example, uncontrollable events. Those you don't know when they will happen. You just know that they might happen when you're in such a state, but you don't know that that necessarily will happen. And this is a really useful property when you model physical systems, because you don't really know what the physical system will do necessarily. So when you model physical systems, you really need this. You need to be able to specify non-determinism. When you specify your control algorithms, on the other hand, you don't want that, right? Because then you say, okay, if the temperature is above 62, I will turn on or off the heater immediately, right? But as we talked about, this hybrid properties, it shows up both in the controller and in the plant. So if we have a generic model to describe hybrid systems, we need to have the ability to specify this non-determinism. Yeah. And when a mode switch happens, when I switch from that mode to that or vice versa, the states might change in any way. So you can have discontinuous changes in our state. So when a mode switch occurs, the state may change discontinuously. Okay, so because of this, that we don't really know when this transition might happen, this model, even if we fix the initial state to a certain value, it might have many different possible executions. So meaning that it is non-deterministic. Okay, so thinking about our state variables, so we have two types here. We have the continuous state variable t, and we have this discrete state variable that in this case describe the two modes. So, state variables, so discrete states, you can call them Q. So it's a mode, and in this case it can be on or off. And we have the continuous states, X, that in this case was the temperature, and it's basically a real variable. Okay, so, and then we have something else. We have this continuous dynamics within each mode here. Okay, so we had a function in every mode here. So we can think about it as from the discrete state and the value of the continuous variables, we will generate a new set of values to our continuous state variables. So you can think about this as a vector field or as described by differential equations. differential equations. Okay, and then we have the initial state. So, and the initial state is a subset of the discrete states and the continuous variables. Right? So you can just notice, compared to how we did it in the discrete event systems course, that in that case the initial state was either a subset or one element of the discrete states. Now you have the continuous states as well to include here. Okay. Then we have the domain that I talked about. So for every state we will have something like 2 to the power of x here. So 2 to the power of x, I think you've seen the notation, the power set. The power set, which is, you can think about this as a set of all subsets of x. Okay, and then we have the edges. So first, we saw that this domain, so this has to be valid for every discrete state we have. So this, you have to be in this set here. Okay, so then we have the edges. So the edges is like transitions in the discrete world. And then we have the guard conditions. Guard, so we can think about them as G. That will, it's a function. So for every edge, it will define this power set of x. So the guard, so t was less than 62, so all values here that are less than 62 will be in this. In this guard condition. So this is just a very general way to describe a hybrid system. And finally, reset map. So this is that, basically think about that as the action in the transitions. So R, so then we have E dot or cross X. So for every edge and every state, we will take us to a new set of states. Like that. So we can easily see that this is a generalization of what you saw in the discrete event systems course. And then, of course, you can start to define the behavior of these systems. So, in this case, with the thermostat here, we argued that there can be many different executions because we don't know when the transitions will happen from different discrete states. But let's assume that we have observed the system now. So then we can start to write down a trace here. So we have T here, temperature and the time on this scale. And then we do something like this. Okay, and then we have the, let's say we have 60, 62, 66, 68, 70, something like that. So let's say we start at some temperature here. What will happen now if we look at the differential equation? So we start in the off mode, and then we will see that K2 is a constant. So if K2 is larger than 0, then we will see that the temperature will go down, right? So let's see. So let's say we have 2.5 here. We have 6.2, So it might be like that. So something like that. And then if we look at what will then happen. So at this point we assume there will be a transition. So now we will switch from off to on, and then the temperature will start to increase again, right? Because we are 70 minus 61, I think is where this will take place. Okay, so the temperature will start to increase up to some point. So, but as we saw from the dynamics here, it will increase at a slower rate when we get closer to 70 degrees. It might be something like that, and then can go down again. Okay, so if we start to write down the trace here, so that's how do we describe the trace for hybrid systems? So we can focus on the mode transitions here. So first of all, so now the state is no longer only the discrete state or the continuous state, right? So, but in this situation, we assume that we started at 66 degrees and we were in the off mode. And then we are in that mode, and what happens with the continuous variables are described by the differential equations. So in this case we will just put on this transition here the time it takes to reach another mode transition. But in 2.5 seconds it will take us to 61 degrees in the same mode. So this is timed action. Okay, and then what happens then? So the guard condition is fulfilled, so a transition might happen, and in this case if we had 61 degrees switched here, let's assume that was the case, then it will switch from off to on, right? So we will then go to on. We will, in this case, we will not anything will happen to the continuous, to the temperature. So we'll have the same temperature here and here. So the reset doesn't do anything here. It just copies the same value. But it will take no time, this transition. So we put an epsilon here. So when we call this for an internal action, which corresponds to a mode switch. Right, and then something will happen again. So I'll draw it down here. And then in this case, in 3.7 seconds, we will reach this. So reach 69.02 degrees or something. And then we will do another mode switch and switch from on to off again. And then it will continue like that. So so this is just one way to write down the trace or the execution of a hybrid system. So, and of course, note, we might have discontinuities in the variables here. Okay, so now we will switch over to an example that we will use for the rest of the day, which is another very simple example, but it has some interesting properties. So it's the bouncing ball. Okay, so it's just a ball, and we have some ground here. It has some initial velocity, v0, and some initial height. Right? I could have brought the ball with me, but you know what will happen. So if I drop the ball, it will start to accelerate, right? By the gravity. And then when it hits the floor, it will bounce. And it will lose some energy in the bounce. Right? So it will not get as high as it was initially. And for every time it bounces, it will lose some more energy. And eventually what will happen? It will go to rest, right? Okay, so, but can we start to describe a model of this? So how would we do it? So we can start with a simple case, right? The ball is in free fall. What are the equations that describe the behavior? So, how many state variables do we need to describe this? So we can have one state variable for the height and another state variable for the velocity. Right? So what will happen to, if you take the derivative of the first state variable, the height, it will be equal to the velocity, right? By definition. And what will happen to the velocity? So that's the acceleration. And that will be minus g. Something like that, right? And in this case, if this is the ground, okay, what is the domain we have here? Yeah, the height should always be larger than 0. Larger than or equal to 0. So this is the domain. Okay, and these are the two differential equations. And we can call this discrete state, we only have one so far, something. So free fall state, right? And we enter this so we can have some initial height and some initial velocity when we start to simulate our system. Okay, so then what happens? So this will describe exactly what happens until we are reaching the floor, right? Then something happens. Okay, it will reverse. The velocity will change, right? So it will change direction, and it will lose some velocity. So we will have higher velocity before hitting the ground than immediately after bouncing. So we can think here, so we have the guard condition that if h is equal to 0, then what will happen? We now do a reset of the state variables, so we can describe what will happen. So the new value of the velocity will be, we have a minus sign because the velocity will change direction, right? We will have some constant here. We call it a. So a will be a constant between 0 and 1. And then we will multiply it with the velocity that was right before it bounced. Like that. Okay, so we can think about it. We can write it exactly as h is equal to 0, or we can think about an alternative way to write it to say that if h is less than or equal to 0 and the velocity is negative, then we will change. So, if we now start to draw an execution of this, or draw a trace here, so we have t. What will happen? If we start with the height, what should happen? Something like that, this, right? And then it will bounce. So it will go up. So then depending on A, but it will not be as high as here, right? It's a little bit lower. And continue like that. Right, so you see, so we call this the height, and if we draw the velocity, what will happen here? So it will, we start with negative velocity, right? And then at this point, the velocity will change. So how will it change? It will go from being negative to being positive. So we see here we will have this, what I talked about, discontinuity in the reset map. So it will be something like this. Right, and then it will go like that. Like this. So this is B of t. So we saw here that this reset map was really useful, because then we can model this discontinuities in the velocity here. So after the break, we will talk about what happens with the bounces here and the time between the bounces. And as you might understand, something very interesting will happen here. So that will be problematic for us. Okay, so let's take a 15 minutes break. Okay, so we will now look at what happens, what time it will take between the different bounces. And I will not go through the calculations here because it's sort of high school physics. Here you have full kinetic energy and no potential energy, and here you have full potential energy and no kinetic energy. So it switches between those, and then you lose some energy in every bounce. Instead, we'll just let's see. So consider the time between the bounces. Okay, so time between bounce I and I plus 1 is given by 2a to the power of I, and then it depends on the initial velocity, or the velocity of the first bounce, and then the gravity. So if A now is a constant between 0 and 1, we can see here that we will this will become smaller and smaller. Right? So the time between the bounces will be shorter and shorter, which is what we expect, right? Okay, so if you now consider n bounces, and we try to summarize the time to do n bounces. So the total time for n bounces what will that be? Okay, Tn. Okay, so we then summarize over these for different i's. So I is equal to 0 to n minus 1, okay, to AIB divided by G. So we see here the only thing that depends on I is this. So V and G doesn't depend, so we can put them before this summation. So 2V over G, and then we have sum of something like that. Okay, so if you remember your geometric sums from your first math courses here, so there you learned that k equals 0 to infinity, a to the power of k is equal to 1 over 1 minus a, under the assumption that a is less than 1. Okay, so if we now look at not a finite number of bounces, but instead an infinite number of bounces. So what will happen? So we let n go towards infinity, and then we will see that we will have 2b over g, and then we will have the sum ai from 0 to infinity, which will be 1 divided by 1 minus a. Right? So if a now is a finite number, so let's say we will get 70% of the speed after the bounce compared to what we had right before the bounce. So then a will be 0.7. Right? So we will have 1 over 0.3 multiplied by 2v over g. Right? So these are constant numbers. So this is something that is strictly less than infinity. Right? It's a bounded number. Okay, so what does this mean? So we considered an infinite number of bounces, and we just observed that we will have an infinite number of bounces in finite time. So the ball Okay, so this is problematic for at least two reasons. first of all, there will be an infinite number of mode switches, which will be complicated if we try to simulate the system, because in computers we can only deal with finite things, right? And it's complicated for another reason, that beyond, what is the system beyond this t infinity? It's not really defined at all, right? So we only have a model up to this point. Okay, so we have some practical problems here. Okay, that's first. So the hybrid system is undefined. Okay, so, and what are the practical consequences for this? And as we will see, we can build a simulation model of this system. But what will happen when you try to simulate it? So it might be that it will have problems with this trying to do very, very frequent bounces. So it will just, the processor will just start to go crazy and use up 100% of the time for an infinite amount of time. Or other strange things might happen as well. So simulation software might crash or give odd behavior. So we will come back to this. So, but what we saw here is an example of something called Xeno behavior. Yeah, and this is the Xeno because of the Greek philosopher with the hair that never caught up with the tortoise, if you remember that story. So it's similar things that happens here. Definition, Xeno execution. So this is what happened. So we had an infinite execution is said to be a Xeno execution if the sum of all timed actions is bound by a constant. So meaning we have an infinite number of mode switches in finite time. So that's what happened with the bouncing ball. Okay, so is this a problem with the physical system, or is this a problem with the mathematical model of the physical system?
Problem with the mathematical model.
It's a problem with the mathematical model. And why do we have this problem? Well, what have we done wrong?
That's a good question.
So this is an ideal bounce, right? That didn't take any time at all. There was no compression of the ball and decompression. So if we built a more careful model, the bounce will also take some time, right? And suddenly the ball will go to rest, right? So it will not continue to bounce for an arbitrary long time. So this showed up because we were not really careful enough. We didn't have an accurate model of the real physical system. But as you saw, you can quite easy end up in these situations if you're not careful. And you will have real problems if you try to simulate these systems. Because then it might crash, you can get strange behaviors, everything. So there is no really easy solution to this problem. So the important message today is that this is something you have to be aware of. This can happen. If you model hybrid systems, you need to look for these kind of behaviors, and then think about how to build a more realistic model. I have simulations. We'll see if we will have time to go through those today. I will show what happens in Simulink when you do these things. There will be surprising things. So it will not only crash, other things will happen as well. But I wanted to say one more thing about hybrid systems that might be a bit surprising. And that has to do with the stability. So, let's say we have two states now, or two modes, I should say, that we are switching between. I have some invariant here. And then, so we have A1 here, and then we have x dot is equal to A2x. And then we have a transition. So when x2 is equal to minus 0.2, x1 it goes back like that, and x is equal to a1x. So now we have a1, or I do it like this. a1 is given by this matrix. Okay, so in this case, the eigenvalues of A1 is minus 1, plus minus, and then we have square root of 1000, and then the imaginary number. So they are both in the left-hand side. Both of the eigenvalues are in the left-hand side, or left half plane. So A1 is stable. Okay, so now if we look at A2, so we change it a bit. Minus 1, minus 1. And then we switch. So we'll have 10 here and minus 100 here. So we see then the eigenvalues here will be the same. Okay, so we can immediately conclude then that both modes are asymptotically stable. Okay, so it would be natural to think if we have two stable systems, we switch between them in something that looks rather innocent, right? The closed loop system should be stable as well. Unfortunately, that's not the case. So if we start to simulate this system, we have x1 here, x2, we have 0 there, 0 there. We have this switching plane. x2 is equal to 5x1, and we have another here. x2 is minus 0.2 x1, and then if we start here, it turns out that we will go like that, and then something like this, like that, in this direction. So we will not go to 0. So, unstable behavior. So it's not asymptotically stable. Okay, so conclusions. So by switching between different stable modes, the connected system might become unstable. On the other hand, the opposite thing might happen as well, that we are switching between unstable modes, and then the way we switch, the total system will become stable. So we can't really rely on analyzing the stability of the individual modes. We need to look at the interaction between the different modes and these switching surfaces. So, by switching between stable modes, the system, and it doesn't have to be unstable, of course, but it might be, may become unstable, and vice versa, as I mentioned. So, you really need something more fancy than just the linear methods to show stability of this. And it turns out that you can try to have different Lyapunov functions, which I think you saw in the linear control system design course. So you can try to show that the energy is decreasing also when you switch in your system. Try to do it that way. But it's not something you get for free. So just be aware that strange things might happen when you start to work with these systems. So let's see. So we have 20 minutes left, and I had some computer simulations that I wanted to share with you. So, because one question is, of course, how can you build up a simulation model of hybrid systems? Oh. So we see, so we have 20 minutes. Yeah, so before I go into the simulation, I just wanted to say a few words about how the computer solves dynamic systems. And this is, you already know, right? So we have some differential equation with some initial value, and then we would like to have some compute what is x for this from some initial time to some end time. And a very straightforward method that you learned also in the first control course is the Euler method. So basically you will approximate to say that when you calculate the next value after some subinterval here is equal to the old value plus the integral of the function, and then you assume that it will be constant throughout this interval that you integrate over. So you take some point, in this case you take the first here you do the approximation. So you set in f of x at point kh here. And then you learned in the modeling and simulation that you can do a little bit better. You can use Runge-Kutta, for example, and then you divide each interval into several different subintervals, and then you combine them in some linear form like that. And then, of course, when you simulate large systems, you don't want to have a fixed step size. You would like the step size to vary. And how it varies depends on the dynamics. So if you have slow dynamics, the system doesn't change very much, then you would like to take large time steps. And if it's a tricky system with stiff differential equations, you need to take smaller time steps to keep the accuracy. So you can have different ways to do that, but you try to keep control over how much the system changes in every time step. So you bound that by some number. So, and I will put these slides on the web as well. So, coming back to the bouncing ball example. So this is basically what we saw here. So just that the notation is slightly different. So y is the height, and y dot is the velocity. And c instead of a here for the describing how much velocity that is lost every time. So we see here that we have the same dynamics as we wrote on the blackboard before, and then we can write this guard condition. So here it says that it should switch when the height is less than 0 and the velocity is negative, meaning that the ball is going downwards, right? And then you change the velocity to this, so change the speed of the velocity. And if we now connect this to what we just saw, and how do we solve this inside the computer? So what is Simulink doing here? So you try to adjust the step size, and the only difference is here that the simulation software doesn't know that something can happen at this, that you have this condition, right? So everything is fine here, so it will try to take a relatively large time step, and at the next iteration in the solver, the height might be below 0 here. So if we simulate this, we might get something like this. Let's see if I can. If you don't trust me, finally. So I will come back to how to build up the simulation model, but we'll just simulate it, and we simulate it for 8 seconds first. Okay, so what happened here is that, you see, this is the height, this is the velocity, and here we saw that it will change velocity, but yeah, it will be at height -1 or something like that. And this has to do with this variable step size, or the step size. Even if you have fixed step size, this could be a problem, right? But we didn't really detect exactly when this bounce happened, right? So if you are not careful, simulate hybrid systems, and you maybe have written a specification that says, okay, the ball should always be above the floor. That will no longer be satisfied by this model, right? Strange. So you need to be careful with this. So if we go back to the presentation. So this is what happened, that we took some step size. So at this step, the velocity was, or sorry, the height was far above the floor, and at the next point in time, it was well below the floor, right? So this is not what we expect from a simulation model like this. So what do we need to do? Of course, we would like to have something like this, where the bounces happens exactly at this. And to get that, let's see if we can use the same simulation model as before. We go into simulation, and then we bring up this panel here, and then
You can't see.
oh, okay, so simulation and model configuration parameters. And then you need to have this zero crossing control here. So you need to enable all, and then there are different algorithms that you can choose between. So non-adaptive is the old version, adaptive is the new version. So if you do that, apply, and then simulate it again. Now we got this behavior, which is more what we expect. So what will happen here is that if we have this enabled, it will try to detect, okay, I took a too big step size, I will try to go backwards and figure out where this zero crossing happened. To solve. Of course, this will always be a numerical solution for these things. It will be an approximation of where it happened, but it will be much better than if you don't have this zero crossing detection enabled. And the problem with, so you can have conditions, or in these maps, you can have conditions related to the time, and the time, of course, that you can feed into the solver directly. But if you have conditions on the states, themselves, the system has to solve the system to know how the states will evolve, right? So it will take extra computer cycles if you have this zero crossing detection enabled to do these things. But it's important if you try to simulate hybrid systems to have it. You see, so I think, we do it like this. So how can we simulate hybrid systems in Simulink? So one way to do it is that you have your state variable, so let's say this is the dynamics that we would like to simulate, and we have some initial value here. So x at time 0 is equal to 2. So if we have x here, and we have this integral block, it means that we have dot x here, right? So and dot x was equal to minus x plus 1. So we can feed it back like that, and then we have x here, and then we have a function that take the minus of that and add 1 to it. And then we feed it into the integrator again. Okay. And if you simulate this, it will work as expected. Okay, but we need a little bit more. So we will take it in steps. So one thing we can do is that we can, if we go, let's see, I can do it in MATLAB instead. You see? Okay, so if I bring it up here, you see, I have a different version of this. Okay, here it is. So if it was done like this, you have the initial condition source, and you say it's internal, then you specify the initial conditions like it was here. So then, it only has one input. But you can set an external input. So you switch it to external, like that, and then you get a second, you see, like that. So then now you can specify the initial condition from the outside, like this. So if you simulate this, you will get exactly what you had before. Okay, so now we wanted to build hybrid systems, so we need to set the initial state. We have the reset map for which we will use this, and we had the transition conditions. So we can add a third input here that will reset this integral block when some condition occurs. And that is what is used here. So this is the model of the bouncing ball. And in this case we have the initial value here. And 10 and 5 means that initially we start at height 10, velocity 5, if I remember correctly. And next time this integral block is reset, we will take the value from here instead. And here it will be computed as a function. And in this case, it for the height just takes the input, first input here, and for the velocity it will take minus, and then in this case the A or C is 0.7 here, and you multiply that with U2, that is the velocity. And then we have a triggering condition here that specifies when it should reset the integrator. And in this case we have specified this condition, so we have that if the height is less than 0 and the velocity is negative, so then we have the multiplication here, so it means and. So when this goes from 0 to 1, or from negative to positive, the integral action will be reset. Okay, and then we have the feedback loop as before here, like that. So simulate it again. You saw that we got this system now. So now we have this zero crossing detection enabled. Okay, but I only simulated this for 8 seconds, so we'll see what happens. I simulate a little bit longer. Oh. What happened? So it will bounce as we expected it to, right? So we'll have shorter and shorter time between the bounces, but then at some point, what happens with the height? It will just fall through the floor, right? Is this what you expected? So what happened here? Why did it do this? So go back to the model again. So here we have the model, and we have this condition here that if this was if we have a rising edge on this condition, we will reset. The problem is that this zero, even though we had this zero crossing detection, it will be a numerical solution to it. So it might very well be that after the zero crossing detection that the velocity will not be exactly 0, or sorry, the height will not be exactly 0, it might be slightly negative still, although we are very, very close to 0, right? And then we will have no more detections of this, right? Because now the velocity will be wrong. So watch out, it's a dangerous world. So yeah, I think there are more things to say about this, but I think with that we end today's lecture, and I hope this got you a bit scared.